Hi everyone. Today we'll define derivatives using limits. To do so, we first need to recall how to find slopes of straight lines. If you would like to try the next exercise on your own, download these notes using the link in the video description. To find the slope of the straight line passing through these 2 points, I compute the difference in the y values of the 2 points and I divide it by the difference in the x values of the 2 points. In our case, that is 16 minus 1 divided by 4 minus 1. This is 15 divided by 3, which is 5. We need to know how to find slopes of straight lines because derivatives are slopes of tangent lines. And today we will formalize the process of finding slopes of tangent lines. Consider the function below. This is a famous function, x squared. Assume that you want to find the derivative of this function at x equal to 1. In other words, you want to find the slope of the tangent line at x equal to 1. Unfortunately, I cannot use the picture of the tangent line to find the slope of the tangent line. And that is because the picture can be imprecise. Maybe the tangent line I drew is slightly too steep, or maybe it is not steep enough. I need a more rigorous way of finding the slope of the tangent line at x equal to 1. Mathematicians thought about this problem for a while, and they came up with the following idea. They said, choose a second point on the graph of the function, for example, at x equal to 4. Then they said to draw a straight line that connects the 2 points. This is not the desired tangent line. This line intersects the graph of the original function in 2 places. We call such lines secant lines. The advantage of the secant line over the tangent line is that it shares 2 points with the graph of the original function. It shares the point 1, 1, and it shares the point 4, 16. And I know that the second coordinate is 16 because when I plug in 4 to x squared, I get 16. Knowing 2 points on the graph of this secant line allows me to find the slope of this secant line. I simply compute the difference in the y values of the 2 points and I divide it by the difference in the x values of the 2 points. And I believe you already computed it in the previous exercise and you said that the slope was 5. The next thing that mathematicians ask you to do is to take this second point and move it closer to the first and then repeat the slope computations. For example, I am going to move this point to x equal to 3. Then I will connect the original point with the new second point. I know that the second point has coordinates 3, 9, which allows me to compute its slope. The slope is the difference in the y values divided by the difference in the x values, which is 9 minus 1 divided by 3 minus 1, which is 8 divided by 2, which is 4. The slope of the second secant line is 4. I can continue this process, and I can move the second point closer here, and then closer here, and then closer here, and compute the slopes of the resulting secant lines. Do you see what happens to the secant lines as I do so? If my second point is here, this is how the secant line looks like. If the second point is here, this is how the secant line looks like. The closer the second point is to the first, the secant line resembles the tangent line more, which means that the slopes of those secant lines should resemble the slope of the tangent line more and more. I did some computations for you. I moved the second point to x equal to 2 and computed the slope. Then x equal to 1.5 and then x equal to 1.1 and I computed all the slopes. I included the results in the table on the left. As the x coordinate of the second point gets closer and closer to the x coordinate of the first point, as the 2 points get closer and closer to each other, the slope of the secant line appears to get closer and closer to 2. And because those secant lines resemble the tangent line more and more, this makes me believe that the slope of the tangent line is 2, which means that the derivative at x equal to 1 is 2. For some reason, when I was choosing the second point, I always chose it on the right side of 1. What would have happened if I chose the second point on the left side of 1? For example, if my second point was here, this is how the secant line would look like. If my second point was here, this is how the secant line would look like. If my second point was here, this is how the secant line would look like. The closer the second point is to the first from the left, the secant lines also resemble the tangent line more and more. I included some computations for having the second point on the left side of 1, and I got that as the second point was getting closer and closer to the first from the left, the slope of the secant line was also getting closer and closer to 2. The limit of the slopes of the secant lines is 2, which suggests that the slope of the tangent line is 2. Before we formalize this process, I have one more comment to make. Note that I could not move the second point all the way to the first, because if I did, the 2 points would merge into 1, and I need 2 points to compute the slope. However, even though I'm not allowed to move the second point all the way to the first, I can move it as close to the first point as I wish and obtain better and better approximations of the slope of the tangent line. Let's formalize this process. I am going to choose first x equal to a on the x-axis. This is a function f. The input a has the corresponding point on the graph of the function with the y-coordinate f of a. Then I need to choose the second point on the x-axis. Because that second point will be moving closer and closer to the first point, I will call it by x. This means that the point on the graph of the function has the corresponding y-coordinate of f of x. Then I draw a straight line through these 2 points, and then I compute the slope of this secant line. And the slope of this secant line is computed by taking the difference in the y values and dividing it by the difference in the x values. So the slope is f of x minus f of a divided by x minus a. Then I want to move the second point closer and closer to the first. In other words, I want to make x go toward a. So I want to take the limit of the slope expression as x gets closer and closer to a. I need the limit as x goes to a of the slope expression. This limit will give me the slope of the tangent line. In other words, it will give me the derivative of the function f at a. Sometimes people use slightly different notation to denote the same thing. They start by choosing the point a the same way as before, with the corresponding y-coordinate f of a. However, instead of calling the second point by x, they call the second point by a plus h. They think about the distance between the 2 points as h. So if the first point is at a, the second point is slightly further than a. It's a plus h. You can think about h as a little bit. The second point is a little bit further to the right in this case than a, so we call it by a plus h. The corresponding point on the graph of the function has the y-coordinate of f of a plus h. I draw the secant line and I compute the slope of the secant line by taking again the difference in the y values divided by the difference in the x values. And I get f of a plus h minus f of a divided by a plus h minus a. A and negative a in the denominator cancel, and I get f of a plus h minus f of a divided by h. This is the formula for the slope of the secant line. Now I want to move the second point closer to the first. In other words, I want to decrease the distance between the 2 points to 0. I want this h to go closer and closer to 0. I want it to disappear or get as small as possible. So I take the limit of the slope expression as h goes to 0 this time, and I get the limit of f of a plus h minus f of a divided by h. This is a different way of denoting the derivative of a at x equal to a. These two limit expressions are the definitions, equivalent definitions, of the derivative of f at a. The derivative of a function f at a, denoted usually by f prime, is defined either by the first limit we wrote or by the second limit we wrote, assuming that the limit exists. If the limits don't exist, the derivatives don't exist. But if the limits exist, the derivative exists, and we define them this way. We will practice using these limit definitions to find derivatives of functions in the next video.